let me start going into the real world of turbulent combustion here. As I said, I would like to start by this question of how do you average results, how do you compare them? We just said that we had two averages. One of them is the Favr average, the other one is the Reynolds average, and the difference is linked to fluctuations. I didn't elaborate too much on fluctuations, but you understand that the fluctuation of a product, of course, is never zero in practice. If these things are correlated, it can be large, it can be even larger than the mean, so you need to include these correlations. The discussion between the Favr and the Reynolds average would not be a big one if these two numbers would be close. I would not even talk about it, but in practice I will show you that the difference between the Favr average and the Reynolds average is pretty large in the flame, and you can do that without even having to do a measurement. You can use a model for that. The most famous model for turbulent combustion for premixed flames is what we call the BML model, for the name of the guys who did that 40 years ago. Ken Bray was at Cambridge, and he's still active actually, probably reviewing some of your papers. So what these guys said, they said if you measure temperature at a point here in a premixed flame, basically a premixed flame is a thin flame front. You know the flame front of this flame is about 0.1 millimeter. So in a premixed flame, either the flow is cold or it's warm. So it means that if you measure reduced temperature, either you have 0 or you have 1. And in the middle here, if you see the time signal, what you see here is that you have a flame passing over you, okay? So either I am in the fresh gas or in the burn gas, and in between I see a flame passing by. When the flame passes by, you have here what you call flame passage times, which are complicated notions, but if the flame is very thin, one thing is clear is that these flame passage times are going to be very small. So you can go to the BML model in which you write that temperature is actually this shape here. So it's either cold or burnt. And in between you have infinitely small passage times. And if you call TB the time during which you have hot gases, and TU the time during which you have cold gases, you can actually derive the Favr average and the Reynolds average. This is what I'm going to do now. So first thing you can do is to compute, for example, the mean temperature in the Favr average way. So what is the average temperature here? It's easy. You have to average over time TU plus TB. And during the time TU, temperature is 0. During the time TB, temperature is 1. Okay? So as a result, the average temperature in a premixed flame is TB over TU plus TB. And by the way, you see that there's a big problem. By the way, we have moved away from laminar flames here. What is really this temperature? This mean temperature, which is the quantity you plot in Fluent, for example. It's not a temperature. It's actually a probability here of having burned gases at this point. Because it's not a temperature anymore. We call it a temperature. But the right way to see this thing is to call it a probability. In other words, the temperature at this point, for example, if the mean temperature is 1600, it really means that it's going from 2500 to 300, and that in the mean, you have 1600. That means the probability that you have burned gases is of the order of 59%. Okay? And so it's not a temperature. And it means also that if you want, for example, to use this temperature to guess what's happening at a wall, you're in a bad shape. It's only a probability to have burned gases at this point. And there are moments where the temperature is going to be 2500. Now you can continue with the BML model to compute the mean density. The mean density will be, during time TU, it will be the unburned density, and during the time TB, it will be the burned density, divided by TU plus TB. If you use the average temperature, you can express it that way. Rho B multiplied by the mean temperature plus rho U multiplied by 1 minus the mean temperature. And you can also compute rho theta, which is what we will need for the Favr average. So same thing, TU rho U multiplied by 0 when you're in the fresh gas, TB rho B multiplied by 1 when you're in the burnt gas. And so this thing is equal to rho B multiplied by theta. And if you combine these two expressions for the average density and the average product of density by temperature, you can compute the Favr average, which is this quantity, and this is what you find. Tau here is the heat release factor. It's the ratio of densities minus 1. Tau is of the order of 5 to 8, okay, in a flame. So you see that you can reverse this relation. You see that if tau is equal to 0, if you have no heat release, fine. And many of you, actually, some of you may be studying constant density flames. That's a good idea, because in a constant density flame, no problem. Okay, no dilatation, no tau, everything is equal. But all the others, unfortunately, they have to face the fact that when tau is not equal to 0, this number is not equal to that one. So the Favr average and the Reynolds average can be very different. So this is a curve here. When you just plot this thing, and by the way, you see the BML model is very powerful. In 2 slides, you can derive the fact that if this is the Favr average and this is the Reynolds average, no heat release are equal. If you have heat release, they can be very different. You know, you can have a 0.2 for the Favr average and a 0.7 for the other guy. So when someone is telling you, here is my temperature profile obtained from a Wands code, you have to say, okay, which temperature profile? Favr or Reynolds? And usually they don't know, because you know, if you're using Fluent, you don't even know which average you're using. So this is a disturbing problem, okay? Now there are more disturbing things. I don't want to go too far there, but if you look in this section in the book, you will see that you can prove easily that the average of any quantity Q, average in the Favr sense, is actually equal to 1 minus theta average, Favr average, multiplied by QU, where QU is the conditional average of Q in the unburned gas. Okay, and then you add theta multiplied by QB. What does that mean? What is a conditional average? Typically, a conditional average would look like this. If you measure the velocity in a flow, which is reacting and turbulent, you will usually find out that the velocity looks like this. You know, at this point you are in the fresh gases, and then suddenly you are in the burned gases, and then it comes back again. So what is the conditional average? Is the fact that you're going to look at the theta signal at the same time. This is temperature, and this will be QU. You will measure the average in the fresh gases, or you will measure the average in the burned gases. These two quantities don't have to be equal. Obviously, the speed, for example, in the fresh gases, when you average turbulence, it will have a certain average, but it doesn't have to be the same as what you have in the burned gases. And so that's making things more interesting. So this is a notion which is called conditional averages, and you can actually use it. I'm going to show you a few examples. I just want to show you here this burner, which is actually the Premixed burner I talked about a few minutes ago. And this is a field here where we plotted the Favr average, this is an LES, minus the Reynolds average. In this LES, you can compute both of them. And you find actually that there are big differences here in this zone. Of course, there are differences in places where temperature is changing. If temperature is constant, no problem. But in the zone where the flame is, which is the zone of interest, U tilde minus U bar can be of the order of 3 meters per second. Now, if you look at the velocity field in this system, you do cuts here. You put lines here, and you plot the velocity profiles. This is the result. You have the experiment, which is in symbols, and the lines are the LES, and this is typically the 3 meters per second error margin. So in other words, when these points are separated by less than 3 meters per second, it could just be that you're not comparing Reynolds and Favr average in both systems. In LES, we know which average we take. Again, you talk to experimentalists, you ask them, is this Favr or is this Reynolds? And they won't be able to tell you. Because it's difficult in an experiment to know exactly how many samples you take. You take random samples. You don't know if they correspond to the weighting that Favr would require, for example. Now, it's not the only problem. Turbulence is about fluctuations, so you would like to compare fluctuations also. Here is getting really complex. So let me just give you an idea of why things are getting complicated here. When you have large density gradients, this will require some care on how you compute fluctuations. So one of the reasons for that is the following. In LES, we use space average results. They are instantaneous. And then we average them in time, if you want the mean. In an experiment, you have the experimental resolution. If you're doing PIV, you have a window over which you average results also. And then you average them in time. If you're doing LDV, it's different. You still have an averaging window, which is the zone where you have a signal, and this zone doesn't have a clear size, but it's also average in some sense. And in the end, what everyone is doing in this room is that we compare time average results of LES with time average results of experiment. First thing you have to realize also is that the time average results of experiments are obtained over minutes, seconds. Time average results of LES are obtained about after milliseconds. So we have another problem of sampling. Experimental data are very well sampled, while LES, by definition, is very expensive, and we cannot run seconds. You know, a typical LES in a combustion chamber, if we run 100 milliseconds, it's going to take us 1 million CPU hours. So you don't do that. In other words, I will show that tomorrow. There's 1 millisecond for one of the computations we were doing last year corresponded to 10 years of CPU on a single processor. So you cannot afford to run for a long time. That's a big problem. So let me try to clear this question here. This is the average signal obtained with LES. Okay, here it's a Reynolds average. It would be the same thing for a Favr average. So you have, for example, temperature, and here you have a filter with this shape typically, which defines the zone on which you're going to average around point X. Now, if you have this LES signal and you average it over time now, so this symbol here means I'm averaging over time, F bar. So you have to remember the bar here means in space, and the brackets means in time. 1/t integral of that. You can derive this thing, you can compute the operators, and you find actually that this is equal to the average in time, average in space. In other words, you can compute the two operators, and you still have the same result. So that's reasonable for the moment. And that means you can compare the mean. You can take the mean obtained from the experiment or the mean obtained from LES, and they should match. But if you want to compare the variance, then it gets more complicated. You can actually derive the variance, typically this will be the kinetic energy or the variance of the velocity. You find when you write this thing is that the true variance of the signal is equal to the variance which is resolved by LES, by the resolved time signal of the LES, and you have what we call a subgrid scale variance that you don't have in the LES. This thing here is called the subgrid scale variance, and this you need a model to evaluate it. So how does that thing translate when you compare experiments and simulations? It means that you cannot compare the variance of an LES with the variance of an experiment if you don't invoke a model for that term. So let me show you an example. This is typically the kinetic energy that you measure in an experiment. So you go in the experiment, you have PIV, LDV, whatever, and you plot a profile in any direction of kinetic energy. Then you go into the LES. The first thing you see in the LES is that it's going to be much more noisy. Why is it noisy? It's noisy because you're averaging only over 100 milliseconds instead of 10 seconds. The guy doing the experiment doesn't care. He can kill you anytime he wants. You know, he can run the experiment for an hour if he wants. You can't. So it's noisy. And usually there's a difference between the two. And the question is, why is there a difference? Well, normally the difference comes from the subgrid scale variance. The subgrid scale kinetic energy is between the two. You see this picture, for example, is wrong. Normally, this curve here, the red curve, should definitely be on that side of the other one, because the subgrid scale variance is a positive number. In other words, if you have an LES, this data is here, you can tell the guy doing the LES is wrong. It's not going to work. Something is wrong. This curve should be less than the experimental value, and the difference between the experimental value and the LES corresponds to the subgrid scale kinetic energy that you can model. But as soon as you need to put a model there, it kind of wastes the interest of comparing things. You're not comparing data to data, you're comparing data to data plus model. And that's a big problem for us. So in most cases, we don't even add this kinetic energy. We just compare the raw data, and we know that there could be a difference because by construction, we're not comparing the same thing. Okay, now I need to start working on the real methods that you use to average, and I will start by averaging methods. When using once or you use LES, the same problem you have here is to average the Navier-Stokes equations. We want an equation for the average temperature, for example. How do we do that? We take the equation for temperature and we average it. And normally we should obtain an equation for the average temperature. Except when you do that, you end up with what we call unclosed terms. So we start from the instantaneous Navier-Stokes equation, and we'll end up with typically terms like this. we'll have, for example, somewhere the product of the velocity by the temperature. If we wouldn't have these nonlinear terms, life would be extremely easy. If, for example, all the Navier-Stokes equations would be linear, if you would only have terms like alpha theta, where alpha is a constant, when you average them, you would find alpha multiplied by the average temperature. That'd be simple. But in practice, it's not the case. In practice, you have a lot of terms like this one, the product of a velocity by a temperature, and since it's a nonlinear product, this is not equal to that. And of course, you've seen that in this term here, we have a lot of exponential. So if you take the average of an exponential, you will see in a few seconds, it's not equal to the exponential of the average. And so the difference now between this quantity and this quantity is what we have to model. We want to express everything in our terms as a function of this quantity. These are the quantities which are the variables for our code. And these correlations, we don't know them, so we want to model them. We need to replace them. So what's the procedure? We start from the Navier-Stokes equations, and we average them. And we need unclosed term. For this term, we need closure models. And by the way, you see we are far away from all the details of kinetics. We're not able to incorporate all this stuff here. So let's start with premixed flames. Supposing that the Lewis number is unity, that you have a single step reaction limited by the fuel. This is what we did for premixed flames. And you are adiabatic condition and constant pressure. In that situation, I've shown that yesterday, you can have only one variable, which is the reduced variable, which is called the progress variable. And sorry, I will call it C or theta, depending, but that in the world of premixed turbulent combustion, it's really the progress variable. Everyone works with that thing, going from 0 in the fresh gases to 1 in the burnt gases. If you look at the Navier-Stokes equations, and you average them, this is what you find. You find that the continuity equation remains what I've shown before, except here you have an average for the density and a Favr average for the velocity. And you look at the momentum, and you look here at the temperature, you see that they really look exactly like the laminar equations, where you would replace the instantaneous value by mean values, except that you have additional terms here. These guys here, and this one here. And these two terms here are turbulent diffusion, and this is the mean reaction rate. And these two terms are what you need to model. And I'm going to show you models now. And I don't want you to be afraid by the way we build models, because this is the way it's done. I think you're going to have a hard time believing how simple this is, but this is the way we do it. So our goal now is that you can write a code where the variables will be rho bar, theta tilde, and ui tilde. If you want to write this code here, you have a problem, because here this is not expressed as a function of the mean variable. So you need a model to express this and that as a function of these quantities. How do you do that? Well, the first thing you look at is the turbulent diffusion term. It's rho u theta correlated average. So you can write it average density multiplied by the Favr average of these things. And how do you model it? You need to model it as a function of things you know. What do you know? Well, you know the mean temperature. So usually you're going to write this thing as a gradient of temperature. It's exactly the same thing you do when you use the turbulent viscosity for the momentum equation. You try to express what you don't know as a function of things you know. So when you do that, the nice thing about this property is if once you include this approximation in your model, you end up with this equation. Instead of having an unclosed term here, you have something which is a function of the mean gradient of temperature, and then you just need to add a turbulent viscosity or a turbulent diffusivity. Normally you say the turbulent diffusivity is equal to the kinematic viscosity, turbulent one, divided by a Schmidt number. Schmidt number here is usually taken equal to 1. Well, you can do that. It's a dangerous operation, and I will show that in a few seconds why it's dangerous. Then, if you look at this expression, you can wonder, how did we get this shape exactly? Well, let me show you how this is done. It's written now with C instead of theta, but it's the same demonstration. We look at a flame where the mean temperature looks like this. Okay, you have to realize that when we show something like this, it really means a flame which would look like that. If you do a DNS, it would be a flame like this, where C equals 0 here and C equals 1 here. And the mean temperature would be 0 here, and as soon as we start feeding some flame elements, it goes up, and it's doing that. So this is theta average. So we need to model now this term, this guy here. How do we do it? Well, people doing turbulent combustion, you know, they are not very subtle. They say, well, this term is 0 here, because here C is equal to 0, so of course its perturbations are equal to 0. And C is also equal to, this term is also equal to 0 here. What else do we have which has the same property? Well, the gradient of C, obviously. The gradient of C is non-zero in the same zone. That's a good model. The second thing you say is that what should be the sign of this thing? Well, you say, well, the sign, it would be good to have a model which has a good sign. Huh? The good units also. So you look at the sign of this thing. So that's a usual problem here. What is the sign of this thing? If C here, this number is the perturbation compared to the mean. So typically, if you are here and you see a positive C, it means you are above this line. You have something warmer than the average. And now the intuition is the following. If you are here and you see something warmer than the average, it must come from the right side, because the warm people are on the right side. So if C is positive here, the perturbation, then the velocity must be negative, and vice versa. So in other words, we know that the sign of C tilde, U tilde here, C prime, U prime must be negative. So that means that we need to put a minus. That's a good model. And then you look at the dimensions and you realize that to have the right dimensions, you have to put a viscosity and a constant here. If you're smart, when you write a turbulent combustion models, you always plug in a constant that you can tune later to make the model work. And this is how this model was built. And believe it or not, it's used in all codes. Everyone. Everyone in LES is using this model, everyone in Variance even more. And if you're using Fluent, you do that every day. Now, why we don't like it? Well, we don't like it, you have to use it anyway. I just want to give you an interpretation of what has been going on here. I didn't mention that before, but you have to remember that turbulence, probably some of you have looked at, taken courses on chaos and bifurcations and all this stuff. You have to remember that if the world of the Navier-Stokes equations would be linear, there would be no turbulence. Okay? Turbulence occurs only because you have nonlinear products of things. And so nonlinearities are the quantities which create turbulence. Now what we did here is that when we average this term, it created another term here which has the same nature. It's a turbulent term, it's an agitation term, it creates turbulence. And then we transport it to the right-hand side. Okay, that's fine, you can take it from here, put it here. But then we transformed it into a viscous term. So the nature now of this term is completely different from what was there initially. Instead of having a term which creates turbulence, we have transformed it into a term which damps turbulence. So this model cannot be accurate. At the same time, we don't really have a choice. I will tell you why in a few seconds. We don't have that many alternatives for that. You can use the BML model to understand what we really did, actually. I've shown you this property here of the Favr average being expressed as the conditional averages in the fresh and in the burn gases. You can use it for this quantity. And you can show that the term that we just modeled is equal to this product of mean temperature multiplied by the mean temperature in the burn gases minus the mean temperature in the fresh gases. How do you do that? Well, you go here, you draw a line here, and you take the mean temperature for all these points. This is called the mean temperature in the fresh gases, and for the burn gases, you do the same thing for the rest. So when you are in the fresh gases completely, the average, the conditional average is equal to the normal average, and vice versa. But in the middle here, these averages depend on how much fuel, how much fresh gases, how much burn gases you have. The interesting thing is that the model which we just wrote is this one, and the BML model tells you that these two things which should be equal is this one. So that really means that the gradient of temperature and the difference of the velocity average in the fresh and in the burn gases should have the same sign. In practice, this thing is not intuitive first. One would expect faster velocities in the burn gases, where this thing says it should be the other way. And this condition is not always satisfied. If it's not satisfied, then we have what we call counter-gradient diffusion. Counter-gradient diffusion also is a big hit in the field of premixed turbulent combustion. It's those cases where the model here just doesn't work. Even the sign is not right. So this is a point which can be investigated in DNS. Actually, DNS is a good way to investigate these questions. We did that a few years ago. That's a very big DNS here. You have the cold gases, the burn gases. The gradient of temperature is positive in this way. And we did two cases, one with low turbulence intensity and another one with high turbulence intensity. This was published in GFM a few years ago now. And when you plot this term which we model, we saw that there was a different sign actually for the low turbulence and the high turbulence case. In other words, for this DNS, we found counter-gradient turbulence, counter-gradient diffusion here, and we found gradient diffusion here. And that really proves that the model which everyone is using is not valid in all cases. At high turbulence intensity, it is valid, and at low turbulence intensity, it's not. So in the end, what you need to remember from that is that everyone is using this model, but there are situations where even the sign of this model will be wrong. You have to know it. But on the other hand, we have not much choice to use this, to replace this model. People have tried to find better models, and for the moment, everyone is stuck with this one. So this is what you will find in the literature. There's not much more to do on that. The only thing you can do is to use a smaller mesh to decrease the importance of this. Okay, let me talk about the second term now, which is even more of a problem. This is the reaction rate. So now we have, yeah.
When you do the model, if you don't have a DNS of the thing, how do you know the portion, the ratio of burn gas?
You don't know. You need to write a model. Again, you need to write a model. The question is, if you don't have a DNS, to know, which portion is in the fresh and which portion is in the burn gases, well, you need another model to tell you that. You can guess, how much is in the fresh and how much is in the burn, for example, just from the mean temperature. If the mean temperature is small, you're on that side. If the mean temperature is larger, on this or the other side. But again, you need to invoke more models there. It's modeling again. You need to guess things. That's the problem. But it's not the worst problem. I'm going to show you the worst problem now. The worst problem is you need a model for this guy. The temperature and the heat release. The heat release has this expression. We have seen it yesterday as a function of the reduced temperature. It's a curve which is like this. And so what we need to do now, we know that if the temperature is here, the instantaneous reaction rate is here. But we don't know the instantaneous temperature. We just know the mean temperature. So we need to guess what the average reaction rate will be. And if you remember your math, you know that if this curve is as linear as that one, it's very difficult to average. So let me show you why. We need to average this curve. I'm going to show you a few models, 5 of them. The first models which I want to show you is the models which never work. And unfortunately, they are used today by a lot of people. Then I will talk about the Eddy breakup model, PDF model, the flame surface model, and the secant flame models. So the model which never works is the following one. It's to say, if we know the shape of the reaction rate, why don't we just plug in the mean directly in the expressions which are here? Okay. We know the instantaneous. We take exactly the same expression for the mean. That's a simple way of doing it. But the problem is that simply stupid idea because the shape rate that we're trying to average is the following. If you plot versus time, the temperature, you have these things. And if you plot the reaction rate, you have this thing. Every time a flame passes in front of you, you have a big spike of reaction rate, and then it goes back to 0. And you see that the mean reaction rate is the average of all these green curves. And for example, here, these two temperature signals have the same mean temperature, but of course this one has much more passages here than that one. So if I just want to use the mean temperature to construct the mean reaction rate, I can't. This thing will never be able to that one. And you can prove it also by doing the math of this thing. I will do it in a second. But in a system like this, which is completely nonlinear, you cannot just plug in the mean in the expression to get the result. You need more information. Now, of course, you can say, okay, I understand that. The only problem is that you're doing something too simple. Why don't you take more points in your Taylor expansion? Basically, what we try to do is we try to look for the mean of this expression. Well, of course, plugging in directly the mean in this expression might be a good idea, but maybe we could take a Taylor expansion of this thing. The exponential here, you can expand it as a function of all the higher order terms. And, well, the terms are a little bit tricky. I don't want to go into the details here. But you end up with this thing. you end up with a model for the mean reaction rate where you have here the means plugged in directly in the expression. So if you look at this term here, this is what we are called the no model contribution, and then you have a contribution of the different non-linearities in the problem. And you can try to use this thing, but in practice, when you do that, you find out that this term is larger than that one, this one is larger than this one, and this one is larger than that one. In other words, it's a desperate attempt because every correlation here is larger than the mean. And so in most cases, you don't do that. There are a few cases where it works. Just want to mention those cases. Atmospheric chemistry is one example where people use a model like that. In supersonic combustion, because the flow time is so fast that you can use it. But in all other cases, no one's using that. It simply doesn't work. So let me jump now to the opposite side. The Eddy breakup model. Eddy breakup model is probably in all codes. If you're using any commercial codes, they have the Eddy breakup model there in one shape or another. The Eddy breakup model is really interesting because it was written by a guy called Spalding, Brian Spalding. And Spalding didn't care about the details, he just saw the big picture. And he said, well, what's important for reaction is to have flame passages for the mean reaction rate. For example, if I'm sitting in the fresh gases here, I have no flame passage, I should have a 0 mean reaction rate. If I am sitting in the burn gases, it's the same thing. The temperature is equal to 1. There is never any flame passing by, so the reaction rate should be 0. And in the middle, here, the reaction rate should be proportional to the number of passages of flame. A very simple idea, okay? It's nothing complicated about that. So he said, can I write a model which accounts for that? How do I count the fact that the flames are passing by or not? Well, there's a simple way to do that. The other quantity, again, in terms of bonding, which is 0 here and 0 here, is the fluctuating temperature, the RMS of theta. It's 0 here because theta is constant, equal to 0, and it's 0 here because theta is equal to 1. So you just write the model where you say the mean reaction rate will be proportional to the fluctuation of temperature. And after that, you introduce a time linked to the number of eddies which lead to flame passages. You suppose also that the flame is thin, and if the flame is thin using the BML method, you can prove that this quantity is equal to that, only with averages, and you end up with the famous Eddy breakup model, which says the following thing. It says there is no reaction rate when the temperature is 0 or 1, and in the rest of the region where there are flame passages, the reaction rate has this shape here, and it's scaled by a constant and by a time. This is the time of the largest eddies, epsilon over k. And you just plug that in your code, and right away, it works much better than the other models. So why is it so? The first thing is that when you do measurements, you can measure the mean reaction rate in an experiment. And you see actually that this is the data obtained in École Centrale in Paris. You see that the mean reaction rate as a function of the mean temperature has definitely a shape which looks very much like x multiplied by 1 minus x. And you here, look at this function, it's x multiplied by 1 minus x. And it's much closer to the Eddy breakup model than what we would do with the no model. The no model would assume a shape like this, and that doesn't work. So we see that the Eddy breakup model captures a lot of the good physics here, the one you would like to have. So it's good, but at the same time, people could say, hey, look, why is chemistry gone? Because, for example, the pre-exponential constant I had in the reaction rate, where is it now? Well, the answer is it's gone. It's in the constant. Okay, it's here. Everything is hidden here. You don't even have the equivalence ratio here. It's gone. So the problem is the Eddy breakup model is that when you run an Eddy breakup model for one flame, you're tuning this constant until it works. You go to another flame, you have to tune another constant. And I remember papers submitted to the symposium 10 years ago where there was a table of the constants to be used as a function of the case, you know. They tabulated the constant. And then at that point, you can say, if I have the flame, I can compute it, but if I don't have it, I can't. So it's not a predictive model. But for certain cases, it can work. For example, if you just change the geometry, but you don't change the chemistry, you fit the constant once, and probably you can use it to extrapolate things a little bit. But this model is really the one you will find in a lot of places. At the other end of the spectrum, you have PDF models. PDF models are what we call the ultimate model. PDF basically tells you that if you want to know what's going on, you shouldn't know only the mean, you should know all the PDF. The PDF is just a way to talk about histograms. We can do that right away here. To give you an illustration of PDF, we can, for example, do the PDF of the size of the people in this room. I cannot do it in feet, I'm sorry, I have to do it in meters. So you take the first guy down there and you ask him what his size is, and he says 1.8, and you put a +1 here. Take his neighbor, he's 1.7, 1 and you add a system like this, and you end up with an histogram of the sizes of the people in this room. And you can do that, for example, for Princeton University, and you will obtain a shape. Okay? How would this shape look like? I've been doing that for 20 years, and it always works. No, it's not Gaussian. I believe it looks like this. Because men are usually taller than women. Depends. That in France, we did it actually in my school in France, and we got 2 bumps here. The idea here is that it shows that it's easy to imagine a PDF, but it's not easy to find the shape of the PDF. As soon as the process gets complicated, guessing what the PDF is the whole game. If you have the PDF, then you have everything. Because, for example, the exact expression of the mean reaction rate is just the reaction rate for a value theta star multiplied by the PDF of theta star, d theta star. And you integrate it and you have everything. So the idea with PDF models is if you have the PDF, you have everything. In practice, having the PDF is the difficult part of the game. To find the PDFs, I won't go into that now because it's not that I don't believe in these things, I just believe they are too difficult for me. There's quite a few good papers, including the last hotel conference last year by Steve Pope, who is really the king of these things. The difficulty really in this problem is to build a PDF. One thing also to realize that I've shown you an example here where things depend only on temperature. But in a real flow, the PDF is the PDF not of temperature, it's the PDF of all the species mass fractions plus the temperature. And so it's a multi-dimensional PDF that you need to guess or to compute. There are methods to do that, and actually some of them are even implemented. I guess Fluent has a modulus for that, but they are very expensive. And what people end up doing, they end up using the Eddy breakup model because the PDF models are so heavy that very few people use them. In practice, however, it's clearly the method to use. This one has no drawback if you can find the PDF. Now, one model which is a good intermediate solution is the flame surface model. Flame surface models are used in multiple places, and for example, piston engines, they are quite often found there. And the idea here is to say that if the flame looks like a flamelet, if it's a surface, you know that the average reaction rate along the surface will be the average consumption speed multiplied by the flame surface multiplied by the density. So if I know these two quantities, I can find the average flame surface. You can do that only if you're in the flamelet regime. That means you shouldn't use this thing if you want to use, for example, a flame which is really turbulent. You shouldn't use this model. But in most cases, in this region, you can use flamelet models. And you will have two quantities to find. The mean consumption speed as C and the mean flame surface. In most models, the mean consumption speed, even so I told you yesterday, is complicated. It depends on the stretch, it depends on curvature, it depends on other things. In practice, what people do, they say the mean consumption speed averaged along this surface is just the unstretched laminar flame speed. That's it. Because it's difficult to do better than that again. So the real problem is not there. The real problem is to find the flame surface density. Because on this quantity you can make a mistake of 20%, but on this one you can make a mistake of 500%. How do you find the flame surface density of a flame? Again here, when I talked about flame surface, it looks like a simple idea. If you want to know really what flame surface are, you need to read this paper of Steve Pope again, and that's going to hurt. This is the equation for the flame surface density. First thing, the flame surface density, the definition is given here. It's not, you always imagine you can just measure a flame surface. It's not that, it is a probabilistic notion. So you need to, for example, here, if you want to find the flame surface, it's the probability of having a given temperature multiplied by the gradient of temperature at this point. gets complicated. Huh? So the equation for sigma is written here. I showed you yesterday the unclosed one. This is the closed one, where you have all the models here. You have the stretch, which appears here. And you have to model this thing. And this is where models get interesting. Let me show you one of the models. For example, this is the coherent flame model, which was initially written at Caltech 40 years ago. So this guy said, for sigma, I'm closing terms with a turbulent diffusion term, a source term, a sink term, and I need model for these things. And this is where things, they were nice until now. And when you reach this point, you need to close these terms. And this is where it gets ugly, because you need to find a solution to close them. So this is an example of how it's closed, for example, for the model which is used at École Centrale in Paris. You put a constant here you put epsilon over k multiplied by sigma as a source term, and here you have a sink term. When these two terms are equal, you find the Eddy breakup model. In other words, at equilibrium, when this equation leads to constant sigma, the model leads to the Eddy breakup model, which is a nice extension of the Eddy breakup model. The problem is also that when you go into the literature, you start looking at models, you find models everywhere, which again shows that no one agrees on what the model should have here. This is just a list of a few models which we tried a few years ago. This is the source term, this is the sink term, and you see that everyone is coming up with a new model. It's like a big game. My model is better than your model. And as I showed before, well, okay, I stopped playing that game a long time ago. I believe it's a desperate game. So there are other ways to do this. One way to do that is to try to resolve the flame movement as much as you can. One solution for that is to use the G equation. So the G equation is this idea that if the flame is not too thick, you might as well say it has a zero thickness and propagate it as an interface with no thickness. The way to propagate an interface is the famous G equation. This equation propagates the signal G at the speed SD. You can prove it mathematically, so that's been used by a lot of people. And it works really well when density is constant, and lots of people have been using it here. And you can see a lot of details on that, for example, in the book by Norbert Peters, and Heinz Pitsch, I suspect, talked about that last year, but you were not here, probably. Numerically, it's a big problem to implement because the density is changing. So you have an interface. Some of you are probably writing codes. You can imagine that if you have an interface on which you should change the density by a factor of 6 over one cell, usually it's an interesting game. And the other problem is that you need the displacement speed, and I've shown you yesterday that the displacement speed was a very difficult quantity to use. So this is why we don't do that. We have tried, and we found it too difficult. So the model we really use in France at the moment is this one. It's the Thickened flame model, which I described yesterday. And the idea here is that if you multiply the flame diffusivity by a factor f, and you divide the flame reaction rate by a factor f, to get the same speed. And since our main problem seems to be spatial resolution, this is a way to make flames make flames thick enough to be resolved on your flame front. I've shown this picture yesterday. This is the unthickened flame, this is the thickened flame. You need much less points here to get this thing to work. Now, of course, if the flame is thin like this or thick like this, it does not react in the same way to turbulence. Obviously, a very thick flame will be almost insensitive to small vortices, while the initial flame was sensitive. So you have to do something about that. And we did that a long time ago by introducing an efficiency function. How did we get the efficiency function? Well, basically, we tabulated, we compared thin flame and thick flames, and we just introduced a correction factor. So how do you do it? Well, you take, for example, this flame here, which is thin, and you make it thicker, and you send it into the same turbulence. So you see this is exactly the same flow, except this flame now has a bigger thickness. So since it's larger, it doesn't wrinkle as efficiently as that one, obviously. So we can measure the reaction rate in these two things and tabulate it as a function of the thickening. And then after that, when we won't have this one, we'll have only that one, we'll know that here we are underestimating the reaction rate by this factor. So you can do that by using DNS and theory, and you end up with an efficiency function which is tabulated here as a function of u prime over SL0 and the integral scale divided by the laminar flame thickness. And once you have that, it's very easy to plug it into your code and run it. And one of the reasons why the secant flame model is used today by a lot of people is just because it's simple. Because I believe, in the long term, only simple solutions are used. Complex solutions do not survive. When the PhD student who wrote the code goes away, the next guy who shows up opens the Fortran code, he doesn't understand anything, and he says, I want to do something else. So it has to be simple. It has to be simple. If you want it to survive, it has to be simple. Now, of course, this is simple. You can make it more complicated. You can even make it dynamic. I won't describe this here. But you should be careful. My students, for example, in France, many of them forget that the model is there. They believe it's working. Well, there's a lot of things hidden in these functions. Okay, it contains a lot of information. I'm just going to show you how the function looks like. It takes 2 lines of Fortran to code it. Okay, you just put here the size of the mesh divided by the flame thickness, U prime divided by SL. You compute this function and you have it. So in the Fortran code, it's easy to forget it's there. And after that, the model goes and works without you, basically. Now, the G equation and the secant flame model are actually very similar. The secant flame model says, I'm going to solve this flame by making it infinitely thin. And the secant flame model says, well, I'm not going to do that because of density variation, etc. I'd like to make it just thick enough that I can solve it on my mesh. In both cases, the objective is the same. You want to propagate an interface at a speed that you know, which is either SL or ST, whatever. And the numerical issues are actually the same. When people tell you that the G equation is solving the flame front over one cell, it's not really true. To make it stable, you need to thicken also the G equation. That's what people don't tell you. Because otherwise the code explodes. It's very difficult to resolve a front which has a shape like that and a jump in density by a factor of 7. So in practice, the objective is the same.
All the variables are not me.
And at that point, yeah, there are still instantaneous variables here. You can do the same thing in LES or DNS. Yeah, but I'm going to show in a second that you can do the same thing with LES. Yeah, the variables. The question was, is this instantaneous variables or is it average variables? The answer is both. You can do it with DNS and with LES. So the extensions of the TF-LES models, there have been quite a few of them, and we use it actually today even when they are diffusion flame. The way we do that is we use this flame sensor ID. The flame sensor S here is something which is 0 when you're far from flame fronts, and it's equal to 1 when you are within the flame front. So the model becomes this one. Now I just want to tell you something else. When I was your age, I was following a course by someone called Bill Reynolds. Maybe some of you have heard of him. He was a professor at Stanford, and he was a specialist of turbulence. So he gave a course which lasted about 5 weeks, trying to write an equation for epsilon, the dissipation, tried to write it, in a rigorous way. And after 5 weeks, he came back and said, it's not working, so I'm going to write it the way I want it to be, because I know how it should look like. So this is when people do that, and they give up on deriving the equation, but just writing the way they want it to be, they call it the master equation. And this is what Bill did. That's exactly what I'm doing here. This equation is not demonstrated here. This is what I would call a master equation. We write it this way because we feel it's the way it should be. We cannot demonstrate it. And there are quite big controversy in the community because now people are trying to demonstrate this equation, but I didn't derive it. I just wrote it because it's the way I think it should be written. But actually, if you look at, for example, look here at this expression for the diffusion, you see something saying it's the normal diffusion multiplied by the sensor plus the turbulent diffusion multiplied by 1 minus the sensor. I'm sure if you take all combustion models today which were for partially premixed flame, you will find something like this, where people say it's something multiplied by that plus 1 minus something multiplied by the other one. You have to make hybridation of models, and it's hidden or it's not hidden, but it is there, believe me. So the way the model works is the following. That's what we call the master equation. That's the equation which we have in our code. Why is it that way? Well, it's that way because if you are in the reaction zones where combustion takes place, the sensor is equal to unity, and this term goes away, and you have this expression, which is the standard secant flame equation, where you know you're going to propagate the flame at the speed that you want. If you have a zone where there's no flame, for example, pure mixing, there you shouldn't mess with the mixing. You should let it work with the normal turbulent diffusion, and this is what the model is doing. if S is equal to 0, this goes away, and you have here dt, which is the normal turbulent diffusion term, so you capture mixing normally in those zones. If you have a very large computer, and you can bring F to 1, in that case, you will just have a resolved laminar premixed flame. If you do DNS, typically, maybe not today, but we've seen, for example, that when the computer size grows, we can put more points, so we can decrease the flame thickness, the flame thickening, and so we go directly to DNS. So with the secant flame model, you basically have just to wait, and every day your computation gets better because you can put more points, so you have less thickening. When you have an ignition region, you can keep this model because the reaction rate will be active, so if the flame must ignite, the model will capture it. Same thing if you have a diffusion flame, and if you are near a wall, this term will go to 0 because it has the exponential temperature effect. So all these things will be done. They will not be done correctly, but at least they will be in the model. So as I said, ultimately, if you wait long enough, the thickening factor will go to 1, you will have DNS. The kinetics are there. You don't need a model for the kinetics. You can incorporate reduced kinetics. And this is the status, for example, this is a big chamber. This is about half a meter here. This is the typical thickening factor which you find. It depends on the size of the mesh, but you see it goes up to maximum value of the order of 40. So that means you make the flame 40 times larger than it is in the real world, but this is pressurized, okay? It's a very extreme case. And it was 200 a year ago. Now it's 40. We believe in 2 years we're bound to 10. And that's, again, it's a lazy man solution, but that works. Okay, I want to finish with a comment on this model, which I call the no model. The no model is making me nervous because we see more and more papers submitted to Commercial Flame or to the symposium where people use the no model. The no model is usually used with a very complicated kinetic scheme. People just take a full kinetic scheme, they put averages everywhere, and they run it. And the very surprising thing is that it gives results. And I want to explain here why it gives results and which kind of results you have to expect. Yeah. So I called it the nut model. The first thing you have to say when you do a model like this is that if you just plug directly your chemical scheme and use average quantities there, you are just trying to resolve a flame front which is 0.1 millimeter with a mesh which is much larger than that. There's just no way you can do it. As I said before, a typical flame front looks like this. If you're using a mesh with a point here, and a point here, and a point here, there's no way you can capture this flame front. So whoever is trying to use the chemical scheme which works for laminar flames in other cases is just not doing it right if he's not using a mesh which is fine enough. And fine enough means you have to be finer than the size of the flame front. This is why we use the secant flame model. We make it thicker so that we can resolve it. But this is not what you do when using the nut model. You just go right away, you plug complete chemistry in your code. So the interesting point is, why does it work? Because normally in a good code, if you try to resolve a front with not enough point, it should blow up. Well, the reason why it doesn't explode is because the code is bad. On another aspect, it has a lot of diffusion. So I'm going to show that in a minute. The equation which is used, for example, for TFLES is that one. If you're using the nut model, you just basically take the laminar reaction rate and you just use here a turbulent diffusivity. Again, by the way, it's very strange that this term is added here and this term is unchanged. Normally, you have correlations in both terms. This should be modeled in exactly the same way that this is modeled. If you use a turbulent diffusion term here, and here you use a laminar term, there's something strange here. And of course, if you would do DNS, you would have a 0 diffusion term here. That would be the right answer. So if you use theory and you try to look at what's going on here, you find out the following thing. You find the flame thickness here of the secant flame model is of course the real thickness multiplied by F. That's the way it was built. For the nut model, you find that this thickness depends actually on dk, the turbulent diffusivity, on the real speed of the flame, but then you have a dt here. And you see the point about that is that this thickness can be large if the dt is large enough. So in other words, this model is also thickening the flame, but it's thickening it in a way which is uncontrolled. It's controlled by the turbulent diffusivity that you put here. And that means also that it's possible for a model like that to be stable just because diffusion is basically taking away all the heat that you produce by the reaction rate. The point is that you're certainly computing a flame, but you're not computing the right one. And if you compute the speed at which you're propagating this front, the speed will be the normal speed multiplied by something which depends on the turbulent diffusivity, which you don't control at all. So you have absolutely no control in this model on the speed at which this thing will move. So if you're using the NUT model, you will resolve a flame, but not the right one. And it will give you a result. That's a nice thing, right? It will give you a result, but if you change the mesh, if you change any model, you will have another result. And that's something that we would prefer avoid if possible. The thing which makes things even worse is that in those codes, usually you also have a very large artificial dissipation. I'll talk about that tomorrow. And if you have a large artificial dissipation, it will also change the flame speed. So in the end, the no model, my advice is really don't use it. And I'll probably stop here before we start diffusion flames, because that's the next topic. So if you have a question, you can take it now. Otherwise, we meet in 15 minutes. Yes?
Just if you could go back, the reaction term you mentioned is a total, it's based on a correlation. So you have this E function that is parameterized by different values of F, the flame thickness.
Yeah, that's for the second flame model. Huh?
Right. So could you just speak to the difference between deriving a correlation for the reaction rate term based on F and having a term for the front thickness that's based on a turbulent diffusivity that's parameterized based on whatever empirical correlation. So like if you just move the term from the reaction rate term to the front thickness term, is that the same? I mean, you're still making an assumption, so.
That's the nice thing about giving a course to people who know the field. Huh? That's just, you're right, there are many choices to do that. You could move everything from here to there. In other words, you could speed up the flame by keeping here the normal reaction rate and bringing everything here. But the point here, if you do that, is that the resolution, the spatial resolution for that term would be crazy. You would need the mesh which matches the real laminar flame thickness, and that doesn't make sense. So you still have to keep the initial idea that the whole thing makes sense only if you resolve the flame front initially. You need to thicken it before you put the turbulence effects there. And the other way to check that this is the right way to do it is that this is a method which is independent of the mesh size, while if you do this one, it will change with the mesh size. The good way to do that, for example, is try to compute a laminar flame. If you try to compute a laminar flame, it's very surprising that people believe they can do that, because if you try to compute a laminar flame with Chemkin, you're going to use adaptive meshes, you're going to use very small meshes, and it's going to be difficult. So why would it be easy now, suddenly in Fluent or codes like this, to use a big mesh and just compute a laminar flame? It's just impossible. Either you put the resolution, or you get the wrong result. But I agree with you. It's actually, this controversy about which term should we use to get the right flame speed is common in the literature. It's actually it's the reason why I'm mentioning it today, because I think people get confused about it. They end up thinking, it's all the same. No, it's not all the same. I believe this is a very bad model, because you are using a model here. Remember, this term can be 100 times larger than that one. So all species will diffuse at stupid speeds here, while here you keep the laminar expression. It's not tuned, it's not compatible. If you're using a laminar reaction rate here, you should use only the molecular diffusion here and not the sum of the two. But it's a tough issue. I believe that I like to control the thickness of the front I'm propagating. So basically, I think this method is based on reasonable ideas. This one is just based on the fact that people doing kinetics don't know turbulence, and they just try to sell this equation as the right way to do it. And there are a few cases where it works, typically diesel engines, for example, because in diesel engines, these terms are negligible. Everything comes from that term, and there is no spatial gradient, so you're fine. But if you go to real engine or to real combustion, this should not be used. It's my advice.
Nice.
Other question?
You also have a similar problem with artificial viscosity with the thickened flame model, right?
Yeah. If you add here artificial viscosity, you also have a modification of the flame speed. But the point is that in that case, it's controlled because this term is usually large enough compared to the artificial viscosity. And again, it's something you can check easily by computing laminar flames. We've done that many times. But you're right, artificial viscosity would also play a role here. I'll talk about that later.
Generally, when you're using LES, you have a fine mesh in pulse. So here comes the problem, like how do you, what is the rule of thumb to take to between the filter size, the mesh size, and your efficiency function, because efficiency function starting from that.
So what's the question exactly? What do we do near walls?
Yeah. So do we make it fine? Because
I'll talk about wall modeling Thursday, I guess. Wall modeling is the weak part of LES in all cases, okay? What kills LES in all cases is that you can model large eddies far away from the wall, but at the wall, since the large eddies are small, you need a fine mesh even at the wall. So at the wall, LES has the same problem for combustion than you have without combustion. What we do for the Thickened flame model, there are modifications of the efficiency function near the wall. Typically, we take into account the fact that turbulence near the wall goes to small scales, so this is included in the efficiency function.
so you basically track the distance from the wall and say the efficiency.
Yeah, you modify U prime and L at the wall. Yes?
Can you explain a little more how you actually calculating the S? That's like a critical part of
I didn't say that. I didn't say it on purpose. It's, the S factor is basically something which should cover the zone where the flame is. So you can either use the reaction rate. What we do usually, we use the reaction rate and then we filter it a little bit more to be sure to cover the zone where the flame is. And there's also a sort of triggering problems there to make sure that you thicken the flame everywhere when it's active, because if you don't, it explodes, okay? If you fail to thicken the flame at a point where there is reaction rate, in our codes, the whole thing goes crazy. So you need to have a sensor which really covers the flame front. I think I had a picture here which probably shows here. Okay, I know the sensor would look a little bit like this one actually. It's covering all the zones where reaction rate takes place.
Does it mean that you're actually tuning that S for the problem?
Yes, sure. You need to define a method to construct the sensor. You can do the full computation with if you are doing a premixed flame, for example, you use sensor equal 1 everywhere. It's only when you do a complex flame, when you need to compute mixing here and flames here at the same time, that you need to introduce this sensor. But again, you're right. There is some tuning in the way you prepare the sensor. And it's important because if you don't do it well, the code will explode. It's described in the papers, usually, the methods to do that. Yes? You mean thermodiffusive? Well, the question is, can you predict instabilities? Depends which instability you're talking about. If it's a thermodiffusive instability, if you're talking about the laminar instabilities that you've seen in the course of Moshe, for example, since you modify the diffusivity, you are basically touching that. And so thermodiffusive instabilities cannot be captured once you have modified this equation. It's out of reach. This is very intrusive. Okay, you have to realize that when you divide the reaction rate by F and you multiply the diffusivity by F, it's bad. Okay, but if you use the G equation, it's the same. If you make it infinitely thin with a constant speed, you're throwing away a lot of things. But this is what you have to do if you want to be able to compute, this chamber. But again, thermodiffusive instabilities, they are gone. You don't have them. You have all the instabilities I will describe tomorrow, probably thermoacoustics. This one you will have, but not the thermodiffusive. This is right. Other questions? Only 7 minutes for the break. So we start again at 11:15, so we can, let's make it 11:20, so we can finish at 12:15 for the photographs. Thanks.